So this will be the fifth lecture out of chapter 1, and this will be the final lecture. So in this lecture, we'll talk about this concept of the scientific method. So first is the basic definition. So scientific method is a general process for advancing scientific knowledge. Basically, this is how scientists think. And it's a very systematic way of thinking and approaching a problem and trying to make new discoveries. So it has discrete steps: observations, framing a hypothesis, and laws and theories, and conducting experiments to test those hypotheses or laws or experiments, or laws or theories. Okay, so an experiment is an observation of natural phenomena carried out in a controlled manner so that the results can be duplicated and rational conclusions drawn. So we'll talk about that in more detail as we go through this lecture. Hypothesis is a tentative explanation of some regularity of nature. So basically, it's a thought process that scientists use to organize knowledge and predict future results. And then a law or a theory. So if something just keeps repeating itself and your hypothesis, basically, as we'll see, you'll do experiments to test your hypothesis. And if you keep getting the same result, then you can formulate a law or a theory. So it's basically just a concise statement, or it could be a mathematical equation about a fundamental relationship or regularity of nature. So the basic steps of the scientific method. So you make an observation. It's like, and then you ask a question. It's like, what's going to happen if I do this, right? So you make a predictions, formulate a hypothesis, make a prediction. I bet that if I do this, this happens. And then you do the experiment to see if that happened. And then if it happened, then you think, okay, I better do this a few more times to make sure I keep getting the same result or the same expected result. And then if you keep getting the same expected results, you make a hypothesis, you do an experiment, and you keep getting the expected predicted results, then you can formulate a theory or a law. Okay, so we'll use some examples to try to illustrate this concept. So how scientists think. So what are some hot topics or controversies, or what are some important areas of research in science? So let's say if you can come up with 4 or 5. So if you want to pause this video and see if you can list 4 or 5 pretty hot topics of research in science, or pretty controversial areas in science. And then we'll see if you came up with the same list that I come up with. And there are many, but we can see how like-minded we are if we can think of some of the same areas that are of importance. Okay, ready to go? So obviously, one of the most important one right now is COVID, right? This disease COVID, how to find a cure for it, or how to find better treatments for it, right? So maybe you need a new antiviral, since it's a virus, antiviral agents, or scientists are always trying to discover new antibiotics, right? If it's a bacteria, to sort of kill the bacteria, or vaccines. So if scientists could develop a new antiviral agent to treat COVID, or a new vaccine to prevent a COVID infection, that would be a great thing right now, right? That scientist would become very famous scientists very fast. And that company who develops it would become a very wealthy company pretty fast. Although obviously nowadays, because of the need for something like this, hopefully it could be mass produced pretty cheaply, so that the profit margin is not what's important, just treating people is what's important, right? But obviously there's tremendous amounts of money being poured into this area of research right now to try to find a treatment or a cure or a preventative medicine. So some other areas of research or topics that are very important in chemistry right now, or science in general: global warming. Maybe you came up with that. So what are the basic questions surrounding this? So one, of course, some scientists are on the fence. Some are fully convinced that the Earth is warming. Some are convinced that the Earth is not warming, it's cooling. So if the Earth is warming, then there's some underlying questions that are importance to that, right? So one would be, is it human activity that's causing it? So this is obviously a huge area of interest right now in trying to answer those questions. And if it is due to human activity, then how do you slow it down, or how do you stop it or reverse it, right? So a huge area of interest right now, and unfortunately, it's become a very politicized question right now as well. So some other areas of interest, maybe you came up with this one: GMOs. What's a GMO? So genetically modified organism, right? A GMO. So what does that mean? That means you change the genetics of something like a crop. Genetically modified corn. Why would scientists want to make genetically modified corn? To make it more pest resistant, for example, or to make it more drought resistant, so that the corn could be, or whatever the vegetable is, could be, or grain is, could be grown in a more harsh environment. Or maybe genetically modified mosquitoes. So this is a real thing. So genetically modified mosquitoes so that they can't reproduce in nature. So that would be used to help control mosquito populations. Why is that of importance? Well, because mosquitoes carry a lot of diseases, right? So if you can decrease the mosquito population, then you could conceivably reduce the amount of diseases that are being spread by mosquitoes. So, and obviously there's controversies around these. So what is the controversy? Well, it would be regarding their safeness. Are they safe for human consumption? Are they safe for animal consumption? Things like that, right? And is it going to create more problems than it solves? So there's always controversy, obviously, surrounding issues like this. Some other things, I just wrote a few down here in case I forgot off the top of my head. Talked about climate change, genetically modified organisms, the need for new antiviral agents, obviously evolution. Be plenty of people still debating evolutionary history, right? And obviously a very controversial topic, fracking. If you know what fracking is, basically injecting fluids into the ground under high pressure to fracture shale rock, and that releases natural gases and makes it easier to pump oil out of the ground. So obviously there will be some controversy around it. One from an environmental perspective, two, could it potentially be causing geological problems? So those are some of the issues in science today. There's plenty that are very important topics, and plenty that are very controversial topics as well. I guess we could have stuck another one on here that's very controversial. Stem cell research, right? So maybe new diseases or new treatments for diseases or cures for diseases could be developed from stem cells, but it's a controversial area of research. So we're not going to try to tackle those on this class because they are extremely difficult problems to solve. Obviously, the COVID problem is a huge problem to solve. Otherwise, it would have been solved by now. Global warming is not an easy thing to study because the Earth is huge, and there are factors outside of the Earth, right? Sun activity that affects global temperatures as well. So these are not easy things to study. Very complex things to study. So finding solutions are typically multi-year task. So let's take something that's conceptually easier to understand and easier to tackle in a chemistry lab, for example. So let's say you work in a pharmaceutical industry. So pharmaceutical industries employ a lot of chemists. What do? Is they develop new medicines, right? So pharmacists dispense medicines, scientists develop medicines and treatments for diseases. So maybe this pharmaceutical company is trying to develop the next antiviral agent to treat COVID, or the next antibiotic, or the next anti-cancer agent, for example. So you don't know a lot of chemistry yet, so let's just take a generic equation. So some molecule A plus molecule B to make molecule C. And let's say C is a new antibiotic. So why is there a need to develop new antibiotics? This is something pharmaceutical companies work on, something that academic labs work on at universities as well, because bacteria become resistant to antibiotics over time, right? So there's always a need to develop new antibiotics. Okay, so if we're going to do this reaction in lab, what yield would you like to make C in? And we haven't talked a lot about, well, we haven't talked about yields at all, but maybe you have some chemistry knowledge, or you can just understand what we're talking about. So would you like to make C in 25% yield, meaning you take A and B, let's say you take, and you're supposed to make a gram of C, but you only make 0.25 grams, so that would be a 25% yield. Or if you're, based on how much A and B you put into the reaction, you're supposed to make 1 gram of C, obviously you would like to make 1 gram of C, that would be 100% yield. So what are some reasons? Why would you like to make 100% yield of C? Why not 25% or 50%? So see if you can list 4 reasons. If you wanted to pause the video, if you're playing along at home, and then I'll give you some reasons. Okay, so some reasons why you would want to make 100% yield of C, more to sell. So if this is a company making it, obviously they want to make some profit off of this, so there's more to sell. Other reasons obviously would be if there's no side products. Then there's no purification. So if you have to purify C from other side products, or if you have some A and B left over, then that's going to take time, and that's going to cost money if you have to purify it. Obviously, if you can make more C, then you can treat more people, right? Or if you have a really high yield of C, then there's less waste, which means less. So there's less purification and there's less waste that you have to deal with. So, you know, what do you do with the waste? You can't just pour it out into a lake or a river because that's going to make the environment toxic. So you have to deal with the waste, which costs money. And so if you can make C in 100% yield, then there is no waste. And you can treat more people. There's more product to sell. It's a win-win-win situation all the way around, right? So this would be one thing chemists do all the time if they're doing reaction, is they try to find ways to maximize the amount of material that they make. So what factors do you think chemists can tweak in order to improve the outcome of a reaction? So see if you wanted to play along at home and pause the video and list 5 or 6 things, what things do you think a chemist can do to tweak a reaction to increase the yield? Okay, so some things that chemists can do is change the time. Maybe a reaction needs to go 5 minutes. Maybe it needs to go 5 hours. Maybe it needs to go 24 hours. Maybe it needs to go a day. Some reactions are fast, some are slow. Maybe the temperature. Some reactions need really low temperatures. Some need really high temperatures, right? You could change the pressure. Some reactions go at atmospheric pressure. Some you have to go to really high pressures to make them work. You could change the amount of light. Some reactions need sunlight to happen, some don't. Obviously, photosynthesis needs sunlight, right, to happen. Other things that you could change is the concentration, or the ratio of A and B. So how much of A and B you put into the reaction, or the ratio of A and B that you put into the reaction, or maybe a catalyst. So scientists are all the time trying to develop catalysts to make reactions more efficient, to make them faster, and to make them go on higher yield. So there's lots of things that you can tweak in a reaction, and this would be one thing that chemists do all the time. Okay, so let's just take 2 variables and tweak those to try to make more of C. So let's just take time and temperature. So we set up our first experiment. So let's say we let this reaction go for 24 hours, and we set the temperature at 50 degrees Celsius, and we get a 65% yield, right? So this is a new antibiotic, and you got it in 65% yield. Is that a good yield? Well, it's a trick question. It's all relative, right? If you are the only person or the only company in the world that can make this antibiotic, that's a pretty good yield, right? Because you are the only one that can sell it. But if there's another company down the road that can make this yield, make this antibiotic in 75 or 90% yield, then your 65% is no good, right? Unless you have different starting materials, A and B, and they're cheaper. If you have cheaper starting materials, then you can take a lower yield, right? But if everybody has the same starting materials and one company can make it in 75% yield and you can only make it in 65% yield, that's not going to be profitable. So you have to find a way to increase the yield. Okay, so then let's do another experiment. So let's do experiment number 2. So let's change the time to 36 hours and change the temperature to 70 degrees Celsius, and we get a 75% yield. So is that a good experiment? You got a higher yield, but is that a good experiment? And the answer is no. That is a horrible experiment. Why is it a horrible experiment? Well, let's look at the definition for experiment. So it's an observation of natural phenomena carried out in a controlled manner so that the results can be duplicated and rational conclusions drawn. So what's the key words in there? Controlled, so it's carried out in a controlled manner. The results have to be able to be duplicated. So if you come back in and did experiment 1 the next day, 24 hours and 50 degrees Celsius, and you can't get 65% yield again, there's a problem, right? And then you have to be able to draw rational conclusions. So let's look at this experiment 2. Is this a controlled manner? And to a scientist, no, this is not a controlled manner. This is not a good experiment. Why? You got a higher yield, but that's the goal. But why is this not a good experiment? Is because you don't know what the increased yield is due to, right? Is it increased to increase time? Did you increase the yield because you increased the time, or did you increase the yield because you increased the temperature? And the answer is you have no idea, right? So you wasted your time. So, does a company want to go to longer times to make a product? No, right? Why not? Because time is money. If you can make it faster, then you can make more product and you have more product to sell, right? Does the company want to go to higher temperatures to do a reaction? The answer is no, right? What would be the ideal temperature to do the reaction at? Room temperature, right here, right? You don't have to do anything. So what's wrong with increasing the temperature? Well, how do you increase the temperature, right? You expend energy, and energy costs money if you have to heat something up. So no, a company does not want to go to longer times and higher temperatures because that costs money. So, but this is a bad experiment just because you don't know what the result is due to. So it's not a controlled. So that's a horrible experiment too, right? So what would be a better experiment too? Let's undo that for a minute. Let's copy that, paste this. So we're going to pretend like we did not do that experiment because a good scientist would never do that experiment to begin with. So we're not going to change 2 things, we're only going to change 1 variable, right? So let's keep the temperature the same, and let's change the time to 36 degrees, and then let's say our yield was 65%. So we increased the time, kept the temperature the same, we got a yield that was 65%. Is this a good experiment? And the answer is yes. It doesn't feel like a good experiment. At the end of the day, you go home dejected. It's like, oh, wasted my time today, right? Tried to get a better yield, spent all of this time doing this reaction, and got the same result. So, but why is it a good experiment? Because you learned something. So you didn't get the result that you wanted, you didn't increase your yield, but you did figure out that increase in the time didn't help any, right? So you learned something. Again, it's a very systematic, scientific method is a very systematic approach to things. You do something, look for a change. If it doesn't work, then you change something else. So what you would want to do now then is, so experiment 2, we didn't get a better yield, so now we go to experiment 3. So now maybe we keep the time the same and increase the temperature. and now we got a 70% yield. So we went from 50 to 60 degrees Celsius. Of course, we don't know that 70 and 36 gave us 75% yield because we never did that experiment, right? So we approach this more systematically, change one thing at a time. So now we got a 70% yield. Is this a good experiment? And the answer is yes. This is a great, it's a great experiment, right? This is the one that makes you feel really good because you got what you wanted, a better yield, and you know why it happened, right? So this would be like hitting, if you're playing golf, hitting the ball on the green. You know, I'm not shooting for the hole, I'm shooting to just make it on the green if I played golf. It makes you feel good once you come back the next day and do it again, right? So that's a great experiment. You got the results you wanted and you know why. So now if you're going to do an experiment number 4, what would you do? So, well, you would do this, right? You draw rational conclusions and so basically you formulate a hypothesis now. So what's your hypothesis? Well, increase in the temperature of this reaction increases the yield. That's a hypothesis, right? And you can predict future events. So if you increase this temperature again, so let's keep the time the same. Let's increase the temperature and we're going to predict that we would get a better percent yield. So we go in lab and do this experiment. We got a better yield, so our hypothesis is right on track, right? And now you keep doing more and more experiments. And eventually, of course, you know, this is not going to turn into a law or a theory because if you increase the temperature too much, eventually you would decompose everything. So you're going to max this out at some point. But this helps you predict and know what to do the next day. Come in and try the temperature higher again and see if you can get that yield even higher, right? So you max out your temperature, maybe you find you get up to 90 and you went beyond 90 and now the yield starts to decrease. So you max out your yield with the temperature. Now we go back and start changing the time. So maybe you change the time, maybe it needs to go lower, shorter amount of time, right? But the point is you approach it in a very systematic way. That's the scientific method. You have an observation, you formulate a hypothesis, go in lab and do some experiments, and then based on the results of those experiments, maybe you tweak your hypothesis a little bit, do more experiments, and if you keep getting the same expected results, then you formulate a law or a theory. So do you know any laws or theories? I'm sure you've heard of some laws or theories. You probably have heard the theory of evolution, for example, or maybe you've heard of Newton's laws if you've ever had any physics classes. So some of Newton's laws, if we just take these as an example, so F equals ma, so force equals mass times acceleration, or distance traveled is velocity times time plus 1/2 of the acceleration times time, right? And then you could calculate how far something would travel. So for a very long time, scientists thought that everything obeyed Newton's law, right? Until better equipment and better instruments were invented. So this is usually the way science works. Better equipment's invented, better instruments are invented, so you can make better measurements, and then you can discover new things, and you can tweak theories and laws, right? So it turns out everything does not obey Newton's laws. So when things that are very small, like atoms, protons, neutrons, and electrons were discovered, or things that are moving very fast, right near the speed of light were discovered, it was found out that they do not obey Newton's law. And so this led to to laws and theories. It led to the quantum theory and the theory of relativity, right? So finally, then, this is basically one principle that all scientists live by. So any true scientist always keeps this in the back of his head, is that one fundamental tenet of the scientific method is that nothing can ever be proven, right? Things can only be disproven. Everything is subject to revision. So that's kind of uncomfortable, right? Because there are no absolutes in science. You just go with the current law or theory until some better experiment or instrument is discovered that maybe allows you to do an experiment to disprove something. It may be that laws or theories that are known now are true and absolute true, but a scientist always keeps in the back of his mind that maybe it's not true. Maybe in the future this could be disproven, right? Okay, so that's it for this chapter.